is April 11th. So today's speakers, like I said, we have Michael Delwiche and Robert Coates. Michael Delwiche is in the Department of Biological and Agricultural Engineering at UC Davis. He received his bachelor's, master's, and PhD all from Cornell. Spent 6 years at Clemson University and then joined UC Davis in 1986, where he's been the department chair for the past 2 years. His research is on biosensors, biological control of plant pest, and sensor systems for precision field control. And that third one is what this talk seems to be in. Robert Coates is also here. He's an associate development engineer, and he's the one who's done the system development for this project. So he'll be participating as well in this talk. Let's give a nice round of applause to Professor Delwiche, please.
Well, good morning or good afternoon, everybody. It's nice to be here. Thank you for inviting me. It's always interesting, the difference in climate between Davis and Berkeley. Davis is pleasant, and you come down here and you shiver a little bit. And I guess you can sort of get acclimated to the maritime climate. I'm going to talk this morning a little bit, give you some idea of a project that we've been working on for the last few years on trying to improve the application of water and chemical fertilizer to plants in various kinds of settings. And it's work that's been funded by a variety of groups, and I'll try to get to that. The folks on, well, Yvette told you what the title of the talk is. Bob, my development engineer, is here, so when I screw up in explaining what he actually did, he will correct me. We're also working with Richard Evans, Lauren Oakey, and Patrick Brown are from Plant Sciences at Davis. And Blaine is Land, Air, and Water Resources. He's really a fertigation person. So see if I can. We got into this problem, gosh, about 3 or 4 years ago, based on a comment that we had from Patrick Brown. He had developed some technology to actually, see if I can get the arrow working on this. I got a button. Let me go back. There we go. I got too many. I have a button on the back of this thing, which is a problem. I have to, all right. He had developed you know what? We'll do it the old-fashioned way. If it works, yeah. He basically had developed technology to do yield mapping in orchards, and he had this about a 20-hectare block of pistachios in which he actually mapped the yield in a particular season. And it's really interesting. If you look, you can see the blue areas here are very low production, 5 kilogram per tree. Over here, you have very high production. And so, I mean, you've got a lot of variation in what you're producing off of this area of land, which means that if you're treating it all the same in terms of water, probably what you're doing is wasting water over here and not applying enough water over here. So you're probably not optimizing your production because you're not giving these guys, these high potential plants, more water, and you're probably giving the low potential plants or these low production areas too much water. Why is there that variability? Where are there going to be difference in soil type, elevation, genetics, even plant-to-plant variations because of differences in grafting? You could have localized pockets of plant disease and even microclimate issues. So basically, you have a lot of spatial variability. And this is a problem not only in orchards, but in nurseries, landscape installations, greenhouses, and we even have now, we're looking at applying some of this technology in vineyards too. So our goal is basically in this work is to improve water use efficiency. There also is the parallel goal of trying to mitigate or prevent fertilizer runoff pollution, percolation into the groundwater. And also, furthermore, if we have some electronics out there, we ought to be able to do a better job of monitoring what's going on with the plants and maybe improving the production. How do we do that? Well, basically, we divide an area, a field, a vineyard, a landscape into much smaller management units, perhaps as much as managing at an individual plant level. Hey, you don't have to go very far to look to see what is done now and how awkward and cumbersome it is. This is just right around our building at Davis. This is one of the irrigation controllers for landscape, and you can see all of the wires and It's expensive to put in. It costs a lot. Furthermore, if you've actually done any field work, having electrical connectors, ohmic connections out in the field is a real problem in terms of keeping it running. And you also have issues with how long a communication length you can have. So we were interested in doing this, perhaps doing this in a wireless way, getting rid of some of the wires. So our global objectives here were to design an intelligent valve controller, an intelligent controller using low power and wireless communication that could actually turn a valve on and off. And we don't have any wires. We have actually no wires, and the only connection to the valve controller is the water. We want to make this standalone, so we have to really worry about the energy management so that, as I said, we don't have external power coming to these. That gets us into developing some kind of a communication protocol between what we call the field controller, the intelligence, and this network of wireless valve controllers. And then eventually, and that's kind of where we are right now, we're almost at a point where we're starting to move some of this technology out of the lab and into several applications to look at various precision irrigation and fertigation strategies. All right, so this is kind of what we're talking about here, where we have this network of valve controllers, intelligent valve controllers, and they're all linked wirelessly to a field controller, and they are clearly they have to be tied into the irrigation line, and in many cases these are polyethylene drip lines. But there also would be maybe a controller at the point where a chemical is being injected into the line. And there are also issues with actually controlling the pump too, because you don't just, I mean, you have to worry about the pump running and the fact that you can't shut off all the valves and still keep the pump running. So we have pump control issues too. So anyways, you have this network of wireless controllers all linked to a field controller, and then eventually maybe there's a laptop there somewhere else. But the real issue is the field controller, and it's talking to the valve controllers. So getting into the particulars of what we did, first objective was to design an intelligent valve controller capable of low power or wireless communication, and that's just kind of it's really been an evolution. We started a couple of years ago just by saying, all right, well, let's explore the idea. So we started with a board from Microchip using Zigbee. Zigbee allows us to use different manufacturers. It was primarily developed for lighting applications. And you can see actually the board that we used here, and then we put it on this is a micro sprinkler stake. This was a kind of a spin-off on a project that originally started on controlling micro sprinklers in an orchard. One of the issues that we had with using this approach was energy management. We need to be able to minimize the amount of energy these things use, and the sleeping routers weren't supported. So we pretty soon migrated away from this technology to the second generation, which was Motive, a company in the Bay Area with TinyOS, the operating system. It was an open source operating system specifically designed for wireless sensor networks. It allowed synchronized sleeping so we could minimize energy use, and you can see the our Motive board down here, and in fact there was our first generation of putting the Motive board in a box with some support electronics and a valve. Other than the fact that Motive doesn't make this product anymore, we migrated away from this technology because of some of the downstream communication issues and lack of capabilities with Motive. And where we are now, and I think where we're going to stay, is with Crossbow. Once again with TinyOS, better downstream messaging, so it really took a lot of the load off of Bob on the software development. And once again, designed for wireless sensor networks. We can have synchronized sleeping. It's interesting when they say sleeping. These things, they sleep, but they wake up 8 times a second. This is not sleep for me. And what we also like about Crossbow is they're very interested in broadening their market, and they're very interested in agricultural applications. And not just agricultural, but in say, urban, nursery, landscape sorts of applications. So that's a good fit because we're interested in trying to get some of these ideas actually out into use. And you can see the small wireless board that we're using from Crossbow. We're using a 900 megahertz version, and actually that's it in a box there, and I'll go through that in just a second. Okay, the schematic of the unit in the box, the Crossbow wireless module is up here. We're going to have we have a small solar panel that's going to harvest energy from the sun, a 200 milliwatt solar panel. We're actually using NiCad batteries, and of course we've got a regulator. And the module has the ability to, we have the ability to take some inputs, external inputs from sensors, and we're going to have things like soil moisture sensors and perhaps temperature sensors, and we could have, well, and another important thing that we need to be able to measure is pressure, water pressure, because that allows us to do, well, you'll see in just a second, I mean, there are a number of issues that require us to know what the pressure is in the water line. But anyways, we have a variety of options for sensor inputs into the wireless module. And then the main output is a pulse to actually switch the valve, turn the water on and off. And notice that I don't say just a valve, but a latching valve, because one of the issues we have here is energy management, and we need to use valves that you can pulse them, and they'll go to a state, and then they'll stay there even if you power them down. And then you pulse them again, and they change state, so that you don't have to constantly powering the valve to turn it on. And that's a real key issue for energy management, and it's also a sticking point in this whole design, because what we find if we look at different manufacturers is there's a real dearth of innovation in latching valve technology. A lot of the technology actually comes from Israel because they're very interested in water conservation and water management there, and the big company is Netafim, and they have a number of latching valves, but there's still a lot of room for improvement. Okay, and the actual box is we have the small 200 milliwatt solar panel. You can see the wireless, the Crossbow wireless module right there. On there, we got some daughter boards from them, and this is our first prototype. So we've just got some FETs in there to do the valve switching, and there's our NiCad battery, which is just a stack of batteries. How many batteries, Bob?
6 batteries.
6 batteries. Okay, so getting to the issue of energy management, we want this thing to be able to operate standalone without external power and to operate all the time in the summer and in the winter and in the sunlight and in the shade. It becomes a little bit of a problem. So we've got a solar panel and rechargeable battery. The microcontroller on the board is low power. We use a latching valve, as I said, so that we don't have to constantly power the valve. And furthermore, we want to synchronize the radio communication so that we're not, because it turns out that using the radio is a big power hog. So we did a little bit of work, with our small solar panel there, just to see if get some idea of how much energy we could actually collect under various conditions, and compare that with what we need to run the electronics. Look at some of we got both current produced and open circuit voltage. But bottom line is, in the sun, we could get anywhere from 50 to 80 milliampere hours from this solar panel. And in the shade, which is probably really where our constraint is, on the order of 6 to 10 milliampere hours. Now, if you compare that with what it's actually using, and you can see here we've got this is a lot of the current the thing draws as it goes through its wake cycles, and once again it's waking up 8 times a second to listen to see if there's any activity on the network. And then if the radio is used, you have a much larger current consumption. But figuring average use of a node, we estimated that per day we need somewhere on the order of 6 to 7 milliampere hours. So we're in the right range. So even if we have these units in the shade, perhaps they're under a canopy, we ought to be able to harvest enough energy to run the things continuously. And that's over here on the right here is a picture of the latching valves. And in fact, we have some of this up in front if you're interested at the end of the talk. So what we've got to do to make sure that we don't run the batteries down is we have to minimize the time we use the radio. And we do that by changing the code. And we also want to minimize, by circuit design, we want to minimize the amount of current the thing draws while it's sleeping. We did some work actually looking at the issue of the batteries staying charged. And so what we did is we took 2 of those valve controller nodes, and we recognized, we've got in the development stage, we've got these things put in plastic boxes with a nice clear cover so that we can see what's going on and it looks cool. The problem with that is the clear cover lets in the sun and it gets very hot in there. So. Which is a problem. So what we did was we did some tests where we just took the boxes and we covered them in paper, and this one's got a little panel that just exposes the solar panel, and we ran some tests to see if the solar panel could keep the battery charged up, and indeed it can over a period of days. You can see that the battery the blue is the battery voltage of the box with the solar panel, and the violet is the battery voltage of the box without the solar panel. So the battery is being depleted. You can see over the days without the solar panel is being charged up with the solar panel. What you can't see very well is the temperature. That's the internal temperature of the box. You can see these daily fluctuations. But notice the temperature scale. And it gets very hot in the box. It got to 40 to 50 C in the box. And I think what we think happened there was that high temperature actually caused the average battery voltage to decrease over time. So we could conclude that the solar charging works, but it probably overcharges the batteries under full sun, and that high temperature is a problem. So clearly in the next generation, we're going to have to shield the boxes from direct solar radiation. All right. Next thing we had to worry about was actually linking all of these wireless nodes together, so to develop a communication network. We're using Crossbow's X-mesh networking, where upstream it uses the best. This network self-assembles and it uses the best route that it discovered, and then downstream the field controller goes in the opposite direction. Our field controller, which is a box that's got a wireless node in it, but it's also got an embedded controller so that we can actually talk to the network. So it's for display and control, and there's a little serial link between the one of the wireless nodes and this single board computer, the embedded controller. You can see it here. We didn't bring it with us. It's kind of bulky. But this is the actual, let's see, where is the, yeah, there's a base node right there, a little wireless node on one of their daughter boards. And then you can see there's our wireless modem and the embedded controller. The wireless modem if we want to link to the laptop, which is useful. And just the embedded controller with an LCD so we can actually talk to the network, and then a battery to run it all. Oh, and I'll probably get lost in the details because Bob's the one who wrote the code, but the actual code running on the valve controller node was basically, it's an event-driven, the node would be powered up and it would do some initialization. And it's as I said, it's event-driven. It might receive a command and then put it in the command queue, or it might actually receive an irrigation schedule and also store that in memory. Or every once in a while, we updated the clocks on the nodes so that everything could keep in synchrony. How often was that done, Bob? Once a day. Yeah. And then over here, the various commands that could be sent were in the command stack to open a valve, to close a valve, to toggle a valve. We might want to toggle a valve because one of the things we're interested in is automated fault detection. So for example, if you had a pressure sensor on a line and you were looking at water pressure and then you gave a command to toggle a valve, if you didn't see any response in the pressure, you'd say, hey, maybe there's a problem. And that's a real issue to somebody in an agricultural operation because they want to be able to find out if there's a fault, if something is not being watered. And what else we got here? And then, yeah, and then there are various commands to maybe an irrigation cycle and to read one of the sensors. Okay, this whole idea of a mesh network, we've got the field controller here, which basically has a wireless node there, and then it's talking to, in this simple example, we've got six nodes, and you power them up, and what they do is you have redundant paths of communication, so that if node 6 needs to talk to the field controller, and this is getting a little bit ahead, and perhaps node 4 goes down, is damaged, in the kinds of things we do, it's conceivable that a coyote would come and eat node 4. The growers are very interested in this kind of stuff, they have these problems. So there are alternative paths for that information to get from node 6 to the field controller. So when everything's powered up the first time, the network is established. You can see that they kind of talk to each other, and the best paths for communication are established. And then if we go from and then upstream routing would be going from a remote to a base. You can see that they're gonna pick the best path to go from where they are to the field controller, and then the base or the field controller communicates with the remote going basically in the opposite direction of those best paths. So if it was going down to node 6, it would go through 1 and 2. And then there would be an acknowledgement from node 6 back up to the field controller that, hey, I got the message. And then what's interesting and what's really useful is that, for example, if let's say node 1 is somehow taken out of the network by a fault, then what you don't have is that the communication path with 4 and 2 and the field controller. And if node 6 then wanted to communicate with the field controller, automatically an alternative route would be selected. So the message would be rerouted. So it makes for a very robust network. This is interesting. Yeah, we're concerned with the range of these things because we could potentially be dealing with fairly big distances, particularly if we're in an orchard. I showed that pistachio orchard. That was, what did we say, 40 hectares, Bob? So that's about 80 acres. Fairly big range. And furthermore, it's through trees, and that's a lot different. Going through trees is different than a visual line of sight. So we did some tests to figure out what the range was between our 900 megahertz Crossbow wireless boards. And we found that the range was very dependent on obstructions, the height of the antenna, the type of antenna, and also whether we had everything stuffed in the box or whether the antenna was sticking up or not. This is hard to read, but you can see some of the various combinations we had. So visual line of sight, or whether we were going through an orchard, and whether the antenna was the whip antenna, which is the little wire antenna that you get with the board, as opposed to a half-wavelength dipole antenna, which is a little more of a bigger deal and not so flexible. And at various elevations from on the ground to a half meter above all the way up to about 5 feet, whether the antenna was in the box or not. The bottom line on that is that if you have the units on the ground and you're in the orchard and you're using the whip antenna, you have a range of 7 meters. That's not very, that's pretty short. That's not the 500 feet that Crossbow talks about. In contrast to that, if you were to say use a dipole antenna in a clear area and get it up a little bit less than 2 meters, we had a range of over 200 meters. So that's kind of the two extremes. What we take away from that in actual building an actual application is that we're probably going to use dipole antennas. We don't think we're going to put them on the ground. We're probably going to put them up about a meter. And that should give us a reasonable range. For areas that are larger than 100 or 200 meters, we have the advantage of multi-hop communication. So as long as one node can be in earshot of the next node, we can hop the message. Okay, we're sort of at a point. I mean, we actually have finished most of the design, and we have our drawings to a PC board manufacturer right now. So we're actually etching some boards, and we're trying to get our system set up so we can do some actual testing out in the field. You've got different issues, whether you're talking about nurseries, container nurseries, or landscape applications, or in orchards. Maybe orchards are not quite as compelling as say greenhouses or nurseries, where you've got a higher value product and you have fewer valves. We also have a project that we're starting on trying to control water in a vineyard. The idea there being to try to regulate the maturation of the crop to bring it up to the same maturation point so they don't have to harvest it so many times, or they can only harvest it once. We have issues with water pressure, maintaining proper water pressure and flow, particularly when we're talking about fertigation, application of fertilizer in the water, because the water pressure determines how much is coming out of an emitter, and also the flow rate is going to determine where the fertilizer front is. We're not at liberty to turn valves on and off willy-nilly, because you've got to worry about what the pump is doing. And whether the pump is, whether there's enough flow coming from the pump. We need to be able to, we think that we need to be able to sense where the fertilizer is in the line and the concentration, so that one of the things we want to do is to be able to apply an exact amount of nitrogen or chemical at a particular location. And unless we know where the fertilizer is in a line and what its concentration, we won't be able to do that. And when I say a line, we could be talking about a half mile or a mile of drip line. So you inject at one point, it doesn't get to the end of the field at the time you inject. There are big time lags, so it's a real interesting control problem. And as I said at the beginning, we're also interested in automated fault detection, so that it can alert an operator. Particularly, this might be very compelling in a nursery application. That there's a problem, there's a group of plants that are worth a lot of money that aren't getting watered. So yeah, and depending on the application, depending on the problem, for example, the nitrogen that you'd be applying via fertigation might be on the order of 100 ppm in nurseries. Or if you were putting nitrogen on in an orchard, it could be a lot higher, many orders of magnitude higher, 10,000 ppm. We've got to worry about what the pressure and the flow rate are, and maybe have some feedback to control the pump. We really have to. There are two ways that you can be injecting chemical into the lines, either passively or with positive displacement injectors, and you can see a dosatron injector here. This is stuff that I'm speaking vaguely about it right now because we're just entering into this phase of the work. But we need to be able to sense where the fertilizer is in the line, and the simplest way we could think to do it would be to actually mount conductivity sensors in the line, and that could be one of the sensor inputs at the node. And you can see down here that we have a small electrical conductivity sensor that we bought from Omega. We did some testing on that just to see whether, okay, is that even going to be realistic? So if we look at the conductivity versus, say, the nitrogen content in ppm for a couple different standard fertilizers, UAN 32 and 20, you can see we get a nice linear relationship, which is encouraging. And this was a 200 microsiemens per centimeter sensor from Omega. So the way we would use this is that we would be looking at the conductivity, and if we saw a big enough change in the conductivity, that could tell the system, the head of the fertilizer front is going by a particular point. And then depending on the sign of that change, the tail went by. I suspect it's not going to be that simple, because I think what's going to happen is over a period of time, the fertilizer is actually going to diffuse in the line too. So there's going to be a temporal effect. But we also think that if we can, these guys they know what they're going to be injecting. So you could probably do a fertilizer-specific calibration, and then from the EC, you ought to be able to get an estimate of what the concentration is. We ought to be able to. So I think that would be a good way to say how much material is being applied at a certain location. Well, that's really where we are right now. We have, as I said, our first, we sort of put things together at the bench level and finish the designs. We're actually having PC boards etched right now. When are they due? A couple weeks. In time to be out there in the spring. We have funding and we have cooperators in orchards and in some nurseries in the Sacramento area. Some interest in landscapes. We'll probably stick around Davis for that. And we'll be looking at various irrigation and fertigation strategies. The people that have supported the work are the California Department of Food and Ag. They have a fertilizer research and education program. They're very interested they're interested indirectly in water. They're interested most directly in fertilizer, efficient use of fertilizer. But they also, there is this sort of regulatory constraint about not over-applying fertilizer and runoff and groundwater contamination. The California Association of Nurseries and Garden Centers, they're very interested in improving the management of the plants in the nurseries, and they're under very strict environmental regulations. And the Slauson Endowment for Ornamental Horticulture. And that's really, tried to be quick about this. Bob's got some of our gizmos there. If you want to, yeah. And maybe, as I said, one of the issues that we have, and we think that actually in terms of commercial development, there's a lot of room for improvement, is maybe not so much in the electronics and the communication, but in the more, and I don't want to even say mundane, but in the different arena of the valving. These are two valves. These are both, is this Netafim too? Yeah, these are both, are they out of Israel or are they out of the? Yeah. So this is a big latching valve. This is a smaller latching valve, but they're still kind of turkeys. And so there's a lot of room for improvement in latching valve technology, which something like this would definitely need, because you can't have 500 valves out there all being powered at the same time.
Well, just to kind of give you an idea, this is actually one of the modes from Crossbow. I'm sure some of you in the audience have done work with this sort of technology before. This is one of their slightly older models. They have a new one out now, but this is what we're using, 900 megahertz, pretty small. You can see that most of it is a battery pack, 2 AA batteries. So power is an issue, and in most cases, I know Crossbow is releasing a product right now for agricultural monitoring, like soil moisture sensors, that sort of thing, that is just coming out right now. And it uses AA batteries, so and solar panels. But power is a major issue. So I think probably the best thing to do is open it up for questions.
Or ideas. Yeah, please.
Okay, well, use the microphone, please.
Yeah.
Actually, I have a question. Since you mentioned it's event-driven, so I'm wondering, you have both the sensing part and the actuator part. So for the sensing part, is that event-driven, or you just pull regularly, like you sample the readings, or there's some sort of a event having, like, say, above the pressure, the water pressure above certain threshold value, then it reports back?
The sensors are just pulled. So right now, the way it's set up is it's just checking the sensors every 10 minutes. But you could have it check any given sensor for any kind of interval you wanted. You could have it's scheduled to check the sensors at a particular time. You could have the field controller send a command to check a particular sensor. There's not an interrupt that occurs due to the sensor at this time. But theoretically, you could set something like that up. But with the low power operation of the system, it makes just as much sense to pull it and wait for, say, your soil moisture content to reach a certain level before you start or stop irrigating.
You have to sort of adjust your time frame, because real time here, if it doesn't respond for 5 minutes or 10 minutes or even a half an hour, that's probably okay.
Can
yes.
I ask one more question? I'm not familiar with X-Mesh, but I'm familiar with BMAC and the Zigbee or IEEE 802.15.4. So is this X-mesh same thing as a contention base? Because you're arguing about how to manage the energy. So I'm just curious whether it's contention-based access or it's time division access for the nodes.
This is why I brought Bob along.
The problem we have with these aren't the nodes that we're using now. They're 900 megahertz, so they're not using 802.15.4. We used Zigbee for a while, which is 802.15.4, right? But the problem we have with Zigbee is that they don't explicitly support battery-powered routers. They require mains-powered routers. So, you know, the idea of having a true mesh network with only battery power, low power synchronized networks doesn't really exist according to the Zigbee standard, as I understand it. Maybe you're familiar with a particular product that does, but I've talked to some of the test houses, and they sent me around to different people, and they didn't know of anyone that was producing a product and writing a stack that supported Zigbee battery-powered routers.
Have you tried the products from the
Dust networks?
Yeah, they have the T-mesh, time division, but they support the battery.
Well, there's this issue of, so even with the Crossbow equipment, the new product that they have, it's a 2.4 gigahertz. You know, there's this issue of being able to overlay Zigbee protocol on top of your own hardware. So Dust, Crossbow, these various companies that are using 802.15.4 compliant chips, it makes sense that they can adopt some of the Zigbee conventions for communication. But that doesn't, does that make sense?
Sorry to interrupt. I think T-mesh, they use the wireless part, which is a different standard than the Zigbee. And they have security features.
Right. Well, maybe we can talk about it afterwards and kind of come to a consensus of what the differences and similarities
Maybe there's
are.
something new, Robert.
Yeah. No, there's a lot of this. A lot of the technology has been. I know that we talked to Dust and you know, considered them as one of our choices, and it's been kind of this evolving process of looking at different manufacturers, different capabilities, and we ended up going with Crossbow, you know, for the basic feature of having battery-powered, you know, low-power synchronized mesh networks. Obviously, yes, I know Dust offers the same thing, but yeah, discussing the particulars of the protocol and stuff like that.
There are other issues too that are actually non-technical, and that is the people who are the other side of it, the people, the industries that fund this work are very interested in actually using something, and if a company is very interested in moving into a market, that makes us very interested in them too. So that's a big vote for Crossbow. Please.
Can you tell us more about the overall strategy for controlling the moisture and the fertilizers level? Because if you want to do it, say, in an orchard on per tree, for each tree, then I guess you have to have a separate water pipe, going to each tree.
That is correct. Yeah.
In which you control the two variables.
Well, you have a polyethylene line that goes down a berm, and in an orchard you would have an emitter, a micro sprinkler, that would tie in with a barb to that polyethylene line.
But then you will not be able to control the, say, fertilizer level going to each tree, but only through the main line. All the trees fed by one line will have the same fertilizer level.
You're correct. We couldn't have a different concentration of fertilizer going to the trees along the same line, so you'd have to change the time. This sounds very much like an argument I had with someone in Haifa last year.
Really?
Yeah. It wasn't an argument, it was a discussion. But I think that I think the real answer is we'll come back in a year and talk to you about that. We're just at that point now.
if you have a concentration of fertilizer in the line and you run one emitter for 5 minutes and the other for 10 minutes, the one that ran for 10 minutes is going to get twice as much fertilizer. But there's other issues of when...
Yeah, but
right.
then the water
So
level
there's
is
a lot
different.
Of these issues of you know,
so he's
putting on water first, putting on water later, you know, how far down into the root zone the fertilizer goes. There's a lot of issues. So it is a very complex issue, and those are some of the things we're trying to look at to see how you can have this site-specific system to manage fertilizer and still address some of the issues that you're talking about. It's pretty complex. You're right.
But he is correct. I mean that you know you change if you change the amount of time that you're applying the fertilizer, you're also changing the water too. So. Yeah.
We have a question here from UC Merced. I'm going to ask it real quick. It says, you mentioned the problem of node failures. Did you perform any stochastic analysis to determine the required number of nodes within communication distance of each other so that all the nodes in the system can communicate to the field controller for a full day, a full week, a full month, etc.?
No, we didn't produce any, we didn't do any modeling or testing for that. You know, part of the problem is, you know, when deploying this into the field, could be any number of nodes, you know, different spacings. So, you know, you'd probably have to check that for, you know, the nurseries and greenhouses, wherever you're planning to install it, whether you'd have an issue there. So right now we're trying to develop a system with, you know, the lowest power, the biggest range possible, sleeping routers, all that sort of stuff to try to make it as feasible a system for a number of different applications.
Yeah, here you go.
Could you describe your valve actuation again? The latching valves. Are they using the same power from the solar cell as the radios, or do you have a separate power source for the valves? And if you do use the same power source, what kind of soak cycles can you support? How many times could you cycle that valve on a day's charge?
Good question.
Actually, the valves themselves, in terms of power, don't take up that much power. You know, you could toggle them on and off many times a day, and that's not going to take up much power. We're talking 50 millisecond pulse from the battery to open or to close it. And the issue is, how many times a day can you do it? I don't know. I'd have to calculate it, but I don't see a reason why you'd be pulsing your valve on and off, you know, hundreds of times a day. You know, when you're irrigating, you're going to irrigate probably at most once a day, maybe a couple times a day for like nurseries or something like that, where you have, you know, small pots. Does that answer your question? Okay.
We do. We have one of the things we do is we have a boost cap on the switching circuit, so that when you do go to switch the valve, there's a nice slug of current there that helps to help you get the valve.
Yeah, this is kind of different than most of the wireless sensor stuff that's out there, where using, like, say, 2 AA batteries, which are 3 volts, and you know, that's dropped. Well, you can use it right off the battery at 3 volts. Sometimes they're dropping it down a little more. But in our case, we need a higher voltage to accommodate the voltage needed to open or close the latching valve. So on the order of 9 to 12 volts.
They're actually 12 volt. They're 12 volt valves, but we find that they can operate on a lower voltage than that and switch reliably.
And so, you know, we regulate that down to operate all the circuit, but then we control the valve directly from the voltage of the battery. And so there's not really issues with voltage drop from the battery causing dropouts in the circuit or anything like that, because it's so much higher than what the circuit actually needs. But that's the problem is, yeah, being able to latch that valve.
I have a question about your sensors or your actuators. It seems like you're sensing mostly the actuator delivery, not the actual what's being received in the soil, like how much water content, what the pH is, what the temperature is, what, I don't know, dew points, all the kind of things. So is that an issue? Or, I mean, I know on the system diagram you had a temperature sensor that seemed to be internal to the board, but nothing that measures the temperature or the amount of light outside. And they're watering in the middle of the day or watering 2 o'clock in the morning kind of stuff. And also, you know, if it rained the previous night, well, perhaps you don't have to water because, you know what I'm saying? So I'm concerned about what kind of sensors you guys have in the soil, so to speak, by each location. Or do you? There's a plethora of sensors you mentioned. There were circles in the block diagram, but they didn't specify what they were.
Yeah. I mean, the sensor that you picked up was you have a temperature sensor inside to monitor the temperature of the node. That's different than what kind of external.
What is the purpose of that sensor? I mean, is that just sort of system,
well,
like I'm overheating, turn me off?
Just to keep an eye on how is the system doing, because as you saw there in the direct sunlight, we had internal temperatures getting up to close to 50 C. So that's a kind of sort of a diagnosis thing that the field controller could keep track of. I mean, that's not the external. We envision we're not at that point yet, but you know we've looked at a number of soil moisture sensors. A very clear thing that we might want to use. Probably ambient temperature. Pressure is a key sensor input. Water pressure. What else, Bob? Do you think?
Well, you know, for the soil moisture, I mean, you're kind of talking about the idea of how are we basing our irrigation control, which in itself is a huge field of study right now.
That's objective 4, man. We're not there yet.
and so, you know, there's, you know, just timed control, you know, and you have to change it. There's using, you know, environmental data like, well, evapotranspiration, but using, like, you know, weather data, that sort of thing. And you know, then of course there's actually measuring your plant or measuring the environment. So soil moisture sensors like watermark sensors are a really cheap one that you can use that work reasonably well if you don't need, like, you know, highly accurate tolerances on your water level. Like the echo probes, those are things you can interface. Some of those you can have built-in temperature sensors on those to measure soil temperature. So there's lots of different ways you can control the irrigation and monitor the environment. And that was kind of, I know we didn't talk about the specifics, but that was kind of all bundled in on the diagram to those sensors that are connected.
But the temperature sensor that you pointed out was the temperature of the box.
Correct.
Yeah.
So do we have any other questions? Okay, well, thank you for coming, sir.
Sure.